let's do something interesting. I hate introductory stuff. Okay, let's see. So I'm going to be doing everything I do in this class off an iPad, which is super cool because it's colored. I'm so addicted to this now. Colors, and I can erase stuff when I can't write and I can't spell. It just disappears. It's like it never was. Love it. So what I want to do is give you kind of a slow and cool introduction to what calculus is. As I think I said before, you've never studied anything like this before. It's a kind of a totally different math. And I want to give you an example of a place where it was cool historically. And what it had to do with is finding the area of a circle. And you and I utterly take that for granted. Like if I say, what's the area of a circle? Most of you have memorized, oh, it's pi times radius squared. But we're just so spoiled in the generations that we live in terms of information. And probably you heard that formula, area of a circle, probably in junior high, middle school for the first time. And you used it to solve problems like this. And let me just illustrate this with something that I think will speak to you. And by the way, you know, my notes, these physical notes make sense because you're sitting here listening to them. When we're all finished with this, if you look at these notes and you think, oh, I'll just skip class today and look at his notes later, they're going to make no sense to you whatsoever. So let's say this thing was, you know, 3 by 2. You would say, well, duh, the area of that is 6. I know to multiply those. That's obvious. And of course, maybe your teacher was annoying back in junior high and said, sorry, the answer is not 6. It's actually 6 square inches. You forgot the units. -1. But why is that? Frankly, they probably were just being annoying. But what does that mean? What does it mean that the answer is actually 6 square inches? Actually, I'd like one of you to ramble about that. What does it mean that the answer is 6 square inches for area as opposed to just a math formula?
Doesn't it identify, like, it identifies the meter of which you're measuring in? So it'd be different if it was 6 inches compared to like 6 feet.
Yeah, like 6 square inches and 6 square centimeters and 6 square feet. Yeah, and that's important because it literally means what it says. If you say 6 square inches, that literally means if this is a square inch, that if you went over here and put 6 of them here, it would actually cover that space up. Does that make sense? I mean, you're literally covering it with squares. That's your only option. Now it sounds kind of weird, but if you took shoes in your room and you put shoes on the ground, you could actually say my room will hold 212 shoes. That's an area measurement. You understand that? It's like you're covering it with something identifiable. It's just that we cover it with squares. Well, why am I bringing that up? Can you appreciate that finding the area of a circle then is going to be kind of tough because you're not. Rectangles, no problem. You can cover rectangles with squares. Well, let me ask you some other introductory kinds of questions. How are you going to do with that parallelogram? That's not going to want to cover up the squares very well.
You cut it up into triangles and squares.
Exactly. Like if you came over here and you chopped this little corner off and then you moved it over here, does it make sense now? It is a rectangle. And so the ancients, if you will, called this squaring. They called it squaring the trapezoid or squaring the parallelogram. They were making squares out of it. And you may understand, as I wasn't looking up to see who said that, but it's like if you have a triangle like this, again, you have a memorized formula for the area of a triangle being 1/2 base times height. But again, you were just told that and you believed what you were told. And a lot of this class is about learning how to think about things that you've seen before, but actually understand them for the first time. And even as something as simple as an area of a triangle, like for instance, if I ask you, why is the area of a triangle 1/2 base times height? Well, that's a little bit tougher of a question, isn't it? Like, can you build that for yourself? And the simple answer to that is if you took this triangle, if you divided this into 2 right triangles and you made a copy of this one and put it right here, and you made a copy of that one and put it right there, does it make sense? That's now a rectangle and it's twice as big as the triangle. And so that's where the 1/2 comes from. And so the point is even if a shape has got angles to it, but they're lines, like it's that you're squaring it, like you're turning it into a square or a rectangle, which is made of squares. And so it's all based on rectangles. But as soon as you got a curve involved, does it make sense? You're not going to be able to do that anymore. So So the ancients, if you will, wondered tremendously. It's like you're looking at this circle sitting here, and they'd say, well, I mean, obviously there's an area. I'm staring right at it. It's an area. So, wouldn't there be some way to find the answer to it? Well, it turns out calculus is the answer to that question. So the area of a circle is pi times radius squared, but that's because someone just told you, you believed them. But it's calculus that gave us that formula. And this is the other reason this is kind of a cool problem, is because you're going to realize that you don't know algebra nearly as well as you need to, because I'm going to go too fast here in a sense, and I'm going to say things that you're going to have forgotten about algebra that you should know but you don't remember. And I wish I could see smoke coming out of your ears, because I would see a lot of smoke coming out of your ears in this explanation because of algebra knowledge. But there was this dude. Have you heard of this dude? That's how you spell his name. And this was his idea. This was Archimedes' idea. And of course, he did this without graphing calculators and even paper and pencil, like sand and rocks to scratch on and stuff. But his idea was this picture that I drew right here, which is, notice that circle. It's like he's saying, let's find the area of the circle. Well, does it make sense if you put a regular, which means all the same length, if you put a regular polygon inside it? This one has 10 sides, so it's a decagon. Mathematicians would call it a decagon. If I put that inside there, does it make sense? It wouldn't be hard to find the area of the decagon. And then of course, that's pretty close to the circle. I mean, except for the fact that we're missing these little chunks out here. So it's going to be too small, but at least it's a decent approximation, right? And the answer is, you can't find the area of a circle. You can't. It's impossible, because you're covering it with squares and it's curved. So you're not going to cover it with squares. It's impossible. Yet there is an answer to it, right? So it's like, how can we get it? So Archimedes' idea was basically this. It's the other thing I like about this, it makes straight lines. Look at this. Straight. I love that. His idea was, if we find the area of that triangle right there, which we know how to do, 1/2 base times height. In this case, that's a 10-sided shape. So there's 10 of those, and it's a regular, meaning all 10 of those triangles are the same triangle. Then I could just find the area of that triangle and say times 10, and I'd have an approximation for the circle, and it'd be a little too small, but at least it'd be an approximation. Well, what do you think Archimedes did after that?
He made the triangle smaller and smaller.
Exactly. Just make the triangle smaller and smaller, or make the 10-sided figure, like make it 20 sides, and then make it 40 sides, and then make it 80 sides. And you can kind of get really close to the right answer then. Does that make sense? Now, if you're a true mathematician, you're about to find out if you are. Will that ever give you the area of a circle?
No, it'll approach it.
John says no. Anybody say yes? I want to see some people are not just staring at me. Anybody say yes? Lots of no's. I saw chat pop up. I saw that one.
I think it does, because wouldn't it reach the limit eventually?
Yeah. So would you agree that so the mathematician would say yes, you will get the area of the circle. The practical person would say no, it's always a hair too small. Now, for 99.9% of humans on the planet, getting an approximation for it is plenty close enough. It's like, why are you doing this anyway? Are you doing it because you're just curious about the universe? That was Archimedes, and that's a true mathematician who just wants to understand. But most people are only doing math because this is a piece of concrete they're about to pour, and concrete costs $100 a cubic yard, and they don't want to order too much and spend too much money, or they don't want to order too little, which is even worse. Now your concrete's short and all screwed up and looks terrible, and you got to tear it all out again. So it's like they're just doing it to get it approximate. And so, an approximation is great. If you're an engineer, engineers hate calculus as a group of people, I should say, because the approximate answer is close enough for them, because all steel isn't the same structural strength. And so to say that steel holds this amount, it's not always the same. And so anyway, do you see the conundrum there, if you will? So let's answer that question. Well, let's do this. So see if you can hang on for this algebra. So to find the area of that, now what I want to do though is not find the area literally of this decagon. I want to find the area as a formula so that I can not let n, the number of sides, be 10. I want to let it be 10, and then 20, and then 50, and then 100, and then 50,000. I want to let n go to infinity. I want to let n get really huge. And Eve was saying, you know, if you let the number of sides get really big, then, you know, does it actually become the area at some point? And that's our question. So I want to let that, I don't want to, I want to use 10 as our picture, but I want to think more deeply than that. Well, you tell me this. If that is 10, if n is 10, you can actually find that angle right there, can't you? Somebody tell us, what would you do to find that angle right there?
And would you use tangent?
Easier than that. We're gonna need trig in just a second, but to find that
Wouldn't you
angle,
just divide the amount of triangles by 360?
yeah, since all the way around is 360 degrees, and in this case there's 10 of them, and it's very important they're all the same. Does that make sense? Again, this is a regular shape. So if I take 360 divided by 10, that's 36 degrees right there. Now, if it isn't 10, it isn't going to be 36 degrees anymore, though, right? It's going to change. And also, one of you mentioned tangent. Like, what does trig apply to? If you hear the word trigonometry, what should you immediately think? Oh, yeah, that's about
Triangles.
triangles. More specifically, though, what kind of triangles?
Right triangles.
Right triangles. So I'm going to split this up into right triangles because then we can use tangent. And here's a place we're going to need it. Like, you speak the language of algebra. You need trig here. There's nobody telling you this. This is just a cool idea that Archimedes came up with, and you just got to have the language of algebra to draw on stuff as you need it. So I'm going to call theta that little sliver instead, which actually makes it now, well, I guess half of 36. It'd be 18 degrees in this picture. Does that make sense? And so, and again, I want this to work for all circles. So I'm gonna call this distance kind of the hypotenuse. That'd be the radius of the circle, right? And I could call that 15 or 27 or whatever, but I want to leave it as r so that I can find the area of all circles. And now you know that the area of a triangle is 1/2 base times height. And so in this triangle right here, then I'm going to take that length right there and call it b for base, and this other side and call it h for height. And now let's see if we can write kind of a big, cool algebra expression that would tell us the area of that 10-sided shape. Well, would you agree that from trig, SOHCAHTOA, the sine of theta is opposite over hypotenuse? So that means b could be written as r times the sine of theta. So that's kind of cool to note. In other words, that length depends on the angle. And then similarly, if I wanted h is the adjacent. So cosine of theta, SOHCAHTOA, cosine is adjacent over hypotenuse. So that's h over r. So that means we could say that h was equal to r times the cosine of theta. So that's kind of important. So now I kind of have expressions for the, what I want here is a formula that has as few of letters as possible. I don't want to have like 5 letters in my formula. I want to have 1 letter, and that's 8. I want it to be n. I want to know how many sides, and then what's the area just as a result of how many sides there are. And so if I just replace those into the formula up there for a, then wouldn't you agree that area is 1/2 times the base, which is r sine of theta, times the height, which is r cosine of theta. To save space, I think I'll just put r squared there. So that's some of the nifty inventions that mathematicians have come up with to save themselves trouble because they're lazy, right? Maybe you remember, I doubt it, but maybe you remember there's some identities. There's an identity that you could replace sine times cosine with something. I would hope that you
Wouldn't it be 1?
vaguely remember. You're thinking of sine squared plus cosine squared when you replace with 1. But there was one that was a sine times a cosine. And so, you know, these are things that should, although you shouldn't have that memorized, you should at least go, yeah, there was ways to rewrite trig expressions, and maybe that'd make my life easier. We don't need those here, but that's just the kind of thing you should think as a person that speaks the language of algebra. And so, okay, great. But a second ago, didn't we say that that angle right there was 360 divided by, well, 10, which was 36, but then we had to kind of cut it in half again. So it's really 360 divided by 20. So then, since we don't want to always have that be 10, does it make sense that'd be 360 divided by 2n? Which is 180 divided by n. And so now what I have is And this is really important in the language of algebra. If I say AN, that should really speak to you. What that should say is, well, I mean, you have to know what A stands for, but it's like area. Oh, area. Yeah, I'm going to find the area. And what is the area a function of? It's just a function of n now. In other words, I don't have b's and h's and thetas. I just have n, and there's only one letter. And so it's only a function of one thing. Now, there's also r, but I'm purposely kind of ignoring that. And I'll show you why in just a second. So in a sense, our sort of final formula for this would be, well, let's see. Oh, I've forgotten something here. What have I forgotten? I didn't do this on purpose, but what is this the area of?
You're missing the other half of your triangle because you
Yeah.
only did the area of one half of your triangle.
Yeah, didn't I just find the area of that? But I want the entire decagon. So what do I still have to do to that I forgot?
Multiply by 2.
Square it.
A little more than 2. What else do I have to multiply it by? Because that's just going to give me the one triangle.
10.
Yeah. So I'm going to scoot this over. I also love being able to do that. So I first have to multiply it by 2 so that now I have all of this triangle, but then I also have to say times 10 because there's 10 of those, right? But again, I'm not going to say 10, I'm going to say n because we want to let that be not just 10. So now, hey, look, cool. Algebra, 2 and the 1/2 cancel. And so now I have r squared times n times the sine of, and we just said a second ago that theta was 180 over n, except for I'm going to use the radian version, and you're very glad that I'm doing this, but you don't know why right now. So would you agree that this is our formula? And so what's amazing is, what polygon does that tell you the area of?
Any.
Any. Like, this is why algebra is cool. Do you understand that? We didn't just find the area of that one decagon. We found them all. That's really cool. And of course, do you understand? I'm sort of ignoring r here because I'm just saying, well, that's a constant. In other words, if you're finding the area of a circle, you're going to know what the radius is. And then you just have to choose, like, what kind of a number should you choose for n if you're going to approximate this? If you want to approximate it using our cool formula that we just made. What kind of a number? I'm asking you to read my mind here, probably. You're probably not sure what I'm asking. What kind of a number? Should I use 2?
I was gonna say a multiple of 10. I don't know. That was just a guess, just because like 10 is easy to deal with.
Yeah, but the most important thing, when you said multiple of 10, the most important thing is just that n is really big. Does it make sense this is going to be terrible if n is 4? Because you're putting a 4-sided shape in there. You're putting a square in there. I mean, like, you have so much missing area. If you take a circle and you say n is 4, like, you're going to miss, it's not even close. Like, you need n to be 20, 50, 100. I mean, big number. That's really key. So I'm going to say here for large n, that's kind of an important. Okay. Now, that seems rather crazy. So I have a couple questions here. So notice we kind of have kind of like 3 things that are being multiplied there. So does it make sense? N is, and I need you to understand this language for calculus, n is on its way to infinity. In other words, we need n to be 100, 1,000, 10,000. Like, the bigger we pick n, the better our answer is, right? So we need n to get huge. That's the math way of saying large n. Large n is English, everybody understands that. An arrow pointing in infinity. Now you got to understand what mathematicians have invented for a language here. So that's as n goes to infinity. Now, can n be infinity? Actually,
No, because you can never get there.
yeah, you can't make it to infinity, which is why those of you who are saying you can't actually get the right answer to this are kind of correct. Infinity is not a number. Every time you pick one, it's never big enough because there's always another one after it. Well, what about the second part of this here? Actually, I'll go in a different, no, I'll go in the same order. What about the sine of pi over n as n goes to infinity? What happens to pi over n for large n? Remember, pi is just a number, 3.14. What happens when you divide by a big number, like 10,000 or 50,000?
It just gets smaller.
Oh,
Yeah, does it make sense? That's on its way to 0. In other words, what you're really doing here is taking the sign of 0. How's your trig? Without a calculator, do you know what the sign of 0 is?
It's 1.
If you memorized it, you could still know it. If you memorized it, you could have mixed it up. Because remember, the cosine of 0 and the sine of 0 were two different answers. And like that should all be a little foggy.
It should be 0 still.
Yeah, so sine, we won't go into this right now, but maybe we'll have a chance to later on. But, you know, and again, this is on that trig sheet. You can cheat and get it off the trig sheet. But a random point, you may remember the x coordinate is the cosine of the angle and the y coordinate's the sine of the angle. And again, I asked you rhetorically, can you build that for yourself? Or is that just a fact you once knew and now you effectively have no idea? Can you make that for yourself? You should be able to based on SOHCAHTOA. If it's memorization, you're going to probably mix those up and have to kind of get it back or look it up. But you don't have to look it up. You just have to know SOHCAHTOA. Well, sine's the y coordinate. So if I'm at 0 radians, then isn't the y coordinate 0? So the sine is, so n is on its way to infinity, but the sine of pi over n is on its way to 0. What about the cosine? That's pretty interesting. What about the cosine of pi over n? Well, we already said that pi over n is on its way to 0. What's the cosine of 0? Oops.
1.
Cosine of 0 is the x coordinate of that point out here, and that is 1. And so the cosine of 0 is actually on its way to 1. And so what are we really multiplying here? We're multiplying infinity times 0 times 1. Do you agree with that? Do you see what I'm getting at? Now that breaks. Do you understand that? So ultimately 1 doesn't really do anything. It's 1. But the question is, who's bigger, 0 or infinity? Is 0 going to win? Like 0 times anything is anything, therefore it's 0. Doesn't matter how big infinity number you pick. If you multiply it by 0, it's still 0. Or is infinity going to win? Because remember, infinity is really huge. And also don't forget, these are on their way there. Like you can't actually get to infinity, nor can you get to 0. So this is on its way to 0, and the other one is on its way to infinity. So what you really have is a fight between a huge number multiplied by a tiny number that isn't quite 0. Who's going to win?
0.
And you'd be making educated guesses at this point. Now, what I want you to do is bust out your nerd machine that Archimedes would have. What would Archimedes have given to have one of these? I don't know. I guess I won't guess.
His kidneys.
Kidneys. You can have my kidneys. How long can I function without being able to pee? So switch your calculator to radian mode, and you'll see in a second why I want you to be in radians. But in this class, we're almost always going to be in radians, and so switch to radians. But what I'd like you to do is take this expression. So remember, the area was r squared times n times the sine of pi over n times the cosine of pi over n. And what I'd like you to do is experiment around with just this portion of it. Like start with 10. Let's all do that just to make sure your calculator is working. So now all we got to do is put 10 in there, and we instantly know that part of the formula for the decagon. Remember, this is any circle because we haven't even chosen a radius yet, but just stick 10 into that. So let's see, I get 10 times the sine of, find the pi button, divided by 10 times the cosine of the pi button divided by 10. I got 2.938. Is that what you got? Now, that seems a little weird because it's like we're sort of beginning the fight of infinity to times 0, but of course 10 is a long way from infinity, right? So now what I want you to do is start putting bigger numbers in there than 10. Start with 99 because you don't have to insert any more numbers. Like put 99 in there. And you all know about the button right above enter that says entry, right? This is a lot to type. So second entry, and then you can just go back and arrow back and retype 99 over the top of your 10 without inserting any numbers. What'd you get this time?
3.13.
Yeah, 3.13. Now go back and insert another 9. So now we have 999 sides. You know how to insert right above delete, second insert, stick another 9 in there. Don't have to retype it, right? You're lazy, I'm lazy, we're all lazy. Actually, we're not
Now we
lazy.
got, it looks like it's getting closer to pi. It's 3.1417.
Yeah, 3.14157. Hey, that looks like pi. Now, if we had done this in degrees, you would not have recognized that, but that looks like pi. So this is crazy. What does it appear the answer is when you multiply 0 times infinity? Incredibly, neither one of them wins. It's like between them. Infinity is so big that it actually pulled it away from 0. Again, my instinct would have been like many of yours, the answer to this is going to be 0, but notice it isn't, it's pi. So 0 is not quite 0, and yet this approaches what in calculus we studied, a limit. It approaches the limit of pi. Now, why are you not surprised that that was the answer to this? For large n, why are you not surprised?
Well, that was the whole point, right?
Because it looks like pi r squared.
You already know the area of a circle, right? You were told it in 7th grade, area of a circle is pi times radius squared. But you were told that by somebody who also probably didn't understand where it came from. Somebody gave it to them, and then they gave it to somebody, and they gave it to somebody. But it came from Archimedes. It came from calculus. We just touched infinity. Like we literally multiplied something infinitely large times something infinitely close to 0. It isn't 0. It's infinitely close to 0. There's a difference. And it turns out that multiplication is pi. And this is where the area of a circle came from. In calculus, what we study is infinity. We touch infinity. We get infinitely close to things, and despite it looking like it would break, it doesn't break. It works. And so for that reason, it's kind of a totally new thing that you would study. And so when people say, I don't need calculus, embarrassing, my answer is, you're probably right. You probably don't. But what calculus has given us is formulas like the area of a circle. So I want to ruin your life, part 1. From now on, go ahead.
For our equation for the area, can't we get rid of the cosine and do sine 2 theta?
Yep, that's one of the identities I was mentioning earlier. Sine of 2 theta is the same as 2 times sine of theta cosine of theta. So you could rework this. You could write that statement in a totally different way. Absolutely. What I would like to ruin your life about is the fact that that statement right there does not say area is approximately equal to pi times radius squared. I mean, that statement says it's actually equal. Like that is the area of the circle, perfect. And it should bother you. Like you're filling a circle with squares here, don't forget that. And yet we're saying we actually have an exact answer for the area of the circle. That's not possible without infinity. Do you understand that? You have to have infinitely many sides to pull this off. Now, another place where mathematicians diverge from kind of most people. When I said a second ago that, hey, doesn't that look like pi? How many of you thought to yourself, well, yeah, it looks like it is, but is it really? Is it just happen to be kind of close to that number? Remember E, 2.718? That was another weird number that exists out there. What if that's just coincidentally close? And if we kept going more sides, like we went to 999,999,000 sides, would it still keep getting close to pi? And even if it does that prove it actually is pi? True mathematicians would say no. The burden of proof still exists, and theoretically we have to come up with some way of determining whether that's the case. And that's kind of a whole branch of math, and ultimately that's kind of what chapter 2 is in the book, which is kind of where we're skipping a chunk of chapter 2, you'll notice as we wade into this. But the concept of a limit is a big concept in what calculus is about, and chapter 2 is meant to introduce that idea to you, but ultimately mathematicians want a proof for this. As I said, for most of us to just look at that and go, hey, look, it looks like it's on its way to pi, good enough for me. I found a formula, looks like it works. All I need is an approximation. If I'm an engineer, to find the area of a circle in the real world, that's all I need. Let's get on with it. Because it's a big jump to actually prove this. You can probably just imagine a little bit that'd be kind of a hard thing to do, and you'd be right. That is a very hard thing to do. So calculus touches infinity. So let's do with the rest of our time now, we're going to have a lot of it. Let's do a quick, let's get into what I want to do the rest of today and tomorrow, which is kind of just start reviewing some algebra concepts. And so I want to give you kind of some random statements here, but I'm also going to show you what calculus has to say about this. So let's see if you can speak the language of algebra. If I told you that f of x was equal to x squared minus 4x minus 7, which is no different than what I just showed you, a of n, right? Except for that was fun because it was area as a function of the number of sides, whereas this is some boring sort of pointless equation. Now, anybody have any answers to this? Why is that actually kind of cool? Is that worth knowing? Did your algebra teacher do a good job? Don't answer, Michaela, because that was me. Who cares? Does anybody actually care about this function? Mathematicians would call it.
Well, isn't it just an even more generalized version of the a of n that we were doing earlier? Like the first equation was for the area of a circle, and this equation could be for anything.
Yes, except for the other one was for the area of a circle particularly, but this is also particular. It's not, this isn't for any shape, it's for a particular shape. What shape is it? You should
Parabola.
Yeah,
Is
kind of
it?
looks like this, right? And when I say it looks like that, that just means if you went and found answers to it and graphed them, you'd get that shape on your graph, right? But whether you know it or not, whether your algebra teacher did a good job or not, like that's the shape of satellite dishes, and that's the shape that planets fly through space in, one of the shapes. And the reason we know when comets are going to return, and the reason we have television signals is because of that shape right there, because it does a good job of focusing the you should have saw this in Math 111, but if a signal bounces off of it, no matter where it hits, it'll bounce to that exact same spot called the focus. But that's a very mathematically precise shape. And when I draw it there, if I said, what did I just draw? Many of you would have said, hey, you drew a parabola, but I didn't really draw a parabola. You know that I meant to draw a parabola, but it's not actually going to do the job of a parabola unless it actually is correct. And it's not going to be correct unless you use this equation to find dimensions, not so much ordered pairs, but dimensions to actually build it. And in the language of algebra, you do things like this. So in the interest of time, I'm going to do this kind of quick. So do you understand that all this is the mathematician's way of saying, oh, okay, you want me to find some points that fit in this equation, and you're saying you want x to be 2, and then this equation tells you what that will spit out, right, for y. F of x is a fancy way to say y. So if I put 2 in there, I get 4 minus 8, which is negative 5 minus, no, that's not true. That is true. 4 minus 8, negative 4 minus 7 is negative 11, right? So that's just like code for if you choose x to be 2, y would be negative 11. So that would just be one of the points on that parabola, right? And at this point, we have no idea which one. And we also might not know, is this parabola upside down or right side up? Again, you should know that from Math 111, but I wonder if you do. What's this person want to know? We're not going to do this, but what's that person want to know? What's that mean in English?
You want to know what y is at 4?
Yeah, if you say y is 4, you're fine to pick y to be 4, but then you got to go find the x that makes that possible. Now, algebraically, what's going to happen to you? I want to answer to this. What's going to happen to you if you try to answer that? That's a harder question, right? That's a harder way to find points. What's going to result from that?
You find 2 solutions.
Yep.
Or no solution.
There'll be 2 solutions to it potentially, like there could be one here at 4 and here at 4, or it could be that the parabola never makes it that high, right? Or it makes it that low, and there might be none. How do you mathematically find those 2 solutions? Because you do realize how much of a pain that is. There's a whole history there too in math, but what's it going to take to find it? Yeah, quadratic formula. It'd be awesome if you had a good pre-calculus teacher. It'd be awesome if you had a program in your calculator. Can you see that? It's kind of a low skills way to do this. But I have a formula there called quadratic, so I can just go in and type 4 in there, and it'll stick 4 into the quadratic formula. It'll stick that equation into the quadratic formula. I'm not going to go into that, but you know, it'll pop the two answers out. I mean, that's the use we're going to make of algebra. We're not going to go back and talk about that, but it's like you need to be able to answer this. Like, it's going to come up from time to time in what we're studying, and you got to be able to go get those other two answers. But this is the kind of the cool way about how algebra works. Now, it turns out, let me show you something kind of interesting. We're running out of time here. I guess I'll end with this. In previous math classes, you found the slope of a line, and you should remember that, oh, that's not that hard. I can find the slope of a line. That's pretty easy. Does a parabola have slope?
Yes.
Yeah, it actually has slope too, and it's actually way more interesting. If you go skiing or ride your mountain bike, do you go down a hill that looks like that all the time? No, it actually undulates and changes, and yet is slope still interesting? Yeah. If you were here on this half pipe, you'd probably be a little scared if you'd never ridden a skateboard before, or if you'd never skied before, or you might be scared there even if you had. Have you ever dropped into a half pipe? They're pretty terrifying, actually. If you're there, the slope can be approximated kind of by that line right there. Whereas if you're down here, does it make sense there's a totally different slope? And on a parabola, it has slope too. It just changes all the time. And of course, you can appreciate that would be good to be able to find that slope. That would be interesting to be able to find that slope. And that's something I'm going to give you later on, is like a mountain bike project where you're going through like a set of doubles and we'll ask you about the slope of the different places you are on that set of doubles that are created by a sine wave and as an application. But it's like slope is a thing way past just lines. Like, this is way deeper than that. But what I want you to realize, and I'll close with this. I might close with this, no promises. Does it make sense if I wanted to know the slope on this bottom one down here? Does it make sense I could actually find it by just picking another point that was close by? And that'd be an approximation. Now, would you agree that I just picked that second point kind of too far away, because wouldn't that give you this slope? But at least it's reasonable, right? But what should I do with that second point? Where should I put that second point?
As close to the other one as possible.
Close as you can possibly get it. Can it touch the other point? Can they be the same point?
No, because then you wouldn't be able to, there wouldn't be any slope between them. There would just be that point.
Yeah, think about this. So if those were the 2 points, you remember how to find slope. Don't you go y minus y over x minus x? And then you get that, which kind of breaks. So it's like it didn't work. And you know, if you look at the picture, the slope is not undefined. Like, I don't know what to call that number. The slope is not broken. Like, it's a number. It's a small positive number, right? And so we can't let the 2 points touch. But it turns out, what did we just do with? Can we let there be infinite many sides to the polygon? Yeah, we can. We just thought approach pi. Can we let those 2 points touch? Yep, in calculus you can. But it doesn't seem like you should be able to. And so we're actually going to be able to find the exact slope at any point that we want to find in a physical sense. That would just be saying, yeah, what's the slope at that point right there? And as soon as you move away from that point, then even a millimeter, the slope has changed a little bit, right? An engineer doesn't care because a millimeter hasn't changed that much. But mathematically, if you move it all away from that point, the answer is different. So we're going to actually be able to let those 2 points, and it turns out that's Calc 1 right there. Find the slope of a curve at any point. That's the entire class. I was kind of like jokingly say, don't tell people this, because this is algebra 1. The problem is that the algebra that we have to do to get the slope at that point is going to be a little bit painful, and we're going to discover some cool shortcuts to where we don't have to do the algebra quite so painfully, and that's what makes calculus beautiful. But you see what we're doing is we're touching infinity again. To get the answer there, what do we have to do with those 2 points? We have to let them get infinitely close. And there's a subtle distinction. Can they be the same point? No, because it just broke. But can they get infinitely close? Yes, they can. And there is a difference. And it turns out that'll produce a number instead of producing undefined and it breaks, like infinity times 0 kind of breaks. But actually, when we let it approach infinity and approach 0, it came out pi, right? Well, we're going to let these two approach each other, and it's actually going to produce an answer to this. And algebraically, as long as you can handle the algebra, that's kind of what the beauty of calculus is about. Secondly, though, it isn't just like, oh, this is why I say it ruin your life. Like the next time you go skiing, I hope that you're skiing and you like stop and you're just pondering like, slope and calculus. And instead of skiing and enjoying the beautiful day like all the other normal people, your life is ruined. That's my goal. But the other side of this is the other side of this is, what if this is a trend? In other words, like what if this is the price of the housing market? Does it make sense the slope is telling you like how much our house is rising, how much our house is rising? Like the slope is a rate of change. It's not just a rise over run. It's actually telling you how fast is your company growing, or how fast is your house losing value if it's dropping off. And so, but the point is that's changing all the time. And the reality of calculus is if you don't know calculus, then nothing in your life can change. And what I mean by that is, like if I said, hey, what's the area of this square? Then you could say I could find the area of that static non-moving square. But what if the square, maybe we'll think of it as like a cell. What if the cell, like cancer, was growing? Well, now you as a non-calculus student have to say, well, as soon as it stops, you call me and then I'll measure it and tell you the area of it. But in calculus, you have to say, well, it's actually changing all the time. Like house prices are always going up and down. They never stop. And so the question would be, okay, well then what is it right now? How much is my house worth right now? And then how much is it changing? Is it positive, increasing in value? No, it's increasing at $1 a year. No, it's increasing at $10,000 a year. No, it's decreasing, $50 a day, $500 a day. So it's what do you have now, and then how is it changing? If you don't have calculus, nothing can change. Everything just has to stay the same. When you look out the window, most things are changing. Trees are actually growing. People are driving down the road. You're getting smarter. You're getting dumber. You're getting taller. You're getting shorter. I'm at the shorter stage. Things change, and calculus is ultimately the mathematics of change. And so that's why finding the slope of something is such a dynamic process. And so in chapter 3 and a little bit leading up to it in chapter 2, that's the very first thing we're going to do, is we're going to let those 2 points come together and see how that actually produces an answer. It's just super cool stuff. Only 4 minutes over. That's a record. Don't forget about that. So you're out of here, and stay after if you want to either ask me anything about the functioning of this course or elaborate on anything I just rambled about. Otherwise, I will see you at 10 o'clock. I'm going to save this and post it to the My Open Mass, so poke around in there, and then we'll happily ever after. See you tomorrow.
Do we need graph paper?
Let's see. That will come up from time to time.
Okay.
If you have a printer, you can just go get some online version of it and print a couple sheets.
Okay.
You won't need a ton of it, but it will help you. We're going to use, I'll probably kick this off with tomorrow, but there's a online graphing calculator called Desmos that's way better than a graphing calculator. It's free. So a lot of times you'll be able to go on there and do your graphing sort of digitally. And what's cool then is you can zoom in and zoom out, whereas a physical graph that you draw is kind of static and stuck there. So hence calculus changes. So some, but not a ton.
The Desmos is awesome.
Desmos is awesome. It's totally true. We'll pick this discussion up tomorrow and we'll show you Desmos real quick, and we'll use it to finish this.
Thank you.
Yeah. See you, Michaela.
Bye.
I had a question about because in some classes, they recommend a certain amount of hours to do to read the book and to work on it. How many hours do you think for maybe an A or B would you say?
That's a good question. It's going to fluctuate, so it's hard to give that, but I'd say a reasonable rule of thumb that I've heard over years is 2 hours outside of class for every hour inside of class. But you'll find that sometimes you don't need near that many because you totally get it. But the way I prefer to think about it, and the reason I get math now is because I run down the rabbit trails. In other words, I'm sitting here trying to do a problem. Well, for instance, today, Eve mentioned that identity about changing sine and cosine. If you heard that and went, oh, I vaguely remember that, I'm going to go look at that. I'm going to go run down that rabbit trail. Even though we're on the way hiking to the waterfall and the goal is to make it to the waterfall, hey, where's that trail go? Well, if you run down that, although that isn't going to help you get to the waterfall, that's helping you know the lay of the land a little bit better. And so it'll take you hours to get to the waterfall. But when you're all done, you'll see the waterfall, but you'll also kind of know the area and you'll have all these other insights. And so although it kind of comes across as a bit of a waste of time sometimes, or it might feel that way, I've sort of made it a pattern when I began teaching, when I realized I took all this stuff and got mainly A's and B's. I didn't really know it that well. And so when I started teaching it, kids would ask me questions like, how come that's, how come sine times cosine is sine of 2 theta? And, I think to myself, I have no idea. But then I ran down that rabbit trail, as a teacher, realizing I should have an answer to that. And so I, built it for myself. And so most of the formulas that exist, I can make them myself. It's kind of the survivalist guy that makes a knife out of a rock or whatever and builds his own hut. The more you do that, the better you'll be at math, and you'll actually be able to use this to make money. And my thing is always think bigger. Like don't think of this like I need to get this stupid class over with so that I can get into that engineering program, which is kind of true. Think, once I get there, I'd like to kick butt. And once I kick butt, I'd like to get a job. And once I get a job, I'd actually like to be good at my job and enjoy the satisfaction of being successful at something and being the one people go to. So it's like, don't look at your life as, I just need to get this over with. Like, run down all those rabbit trails. Is it going to cost you 4 hours outside of class instead of 2? Yeah, maybe 8. But that will pay you dividends, and you'll actually know what the heck you're talking about. So, but you got to balance it. You got other classes, and math's not the center of your universe and all that. But as when you have time and when you have questions that arise, like the more you can waste time there, the better.
All right, thank you.
Mm-hmm.
I have a question.
Yeah, go ahead.
Do you recommend any like practice books? Like I know you have like the syllabus with like videos, but do you recommend like any practice books outside of it?
I think the best way to learn is a little bit more of reverse engineering. Like you can get some kind of an online college algebra book. There's a site called Open Education Resources, OER books. Those are books that people have written that they're putting out there for free. And so you could get a college algebra book and work your way through that. But in terms of like value for your time, if you went into a video series by somebody that was kind of teaching like I did today, just somebody that's teaching. There's a guy called Professor Leonard. He's kind of he's a good calc. I'll mention this to you because he gives really good calc lectures. He's interesting. He explains it simply. But listening to somebody just do a problem and reasoning with them is actually more efficient.
Yeah.
I think so. Finding a playlist on YouTube of somebody that you connect with, and that's different for every person. It's probably more efficient use of your time. Khan Academy, I think, is great. I think he's always teaching for understanding, not just like memorize things. He's teaching for understanding. He's super easy to listen to. He has just kind of his tone of voice, the way he carries himself. He makes mistakes. But if you go into a college algebra playlist for Khan Academy and then start watching your way through those just as you have time, when you got 10 extra minutes, watch a couple of those. That kind of stuff will pay you dividends. But overall, if you just let the class dictate that, in other words, we're like next time I'll be showing you something that mathematicians call composition of functions, which I could sit here and say, you already know this, but the reality is you're going, I don't even know what you're talking about. I forgot. I don't know what that word means. You probably do, but you just don't remember what to call it. And so, when that topic comes up, it's like, ding, 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 there's something you don't know. So now go look at the video series, but look for composition of functions and watch those videos. Like watch it in the order that calculus showed you that you now have a hole in algebra. The problem is it's just too big. Like if I say go back and review everything you know about algebra.
Yeah.
So,
okay. And then what was the professor's name again?
Professor Leonard, Leonard. I think I watched his calculus. I watched a ton of his calculus videos this summer when I was teaching Calc 4 for the first time. And I watched those to, get a deeper conceptual understanding myself. And that's the best way to learn is by reverse engineering and just watching somebody do examples and you looking for the patterns. Oh, I see how to do that kind of problem now. He just has a cool way about him.
Okay. Thank you so much.
Yeah. Good to meet you, McKellen. Keep going. What else is bugging you?
I think they sort of asked a couple of the questions I was gonna have to, like, what would be good reviews on things, because I'm very rusty on my algebra and trig and everything like that too. So
Yeah, I'd still say Khan Academy is my number one, even though that's one everybody knows. But yeah, I actually I was watching Professor Leonard's, and he's must be a total fitness nut, because he literally looks like Clark Kent, and his little YouTube thing is like him opening up his shirt and he's got an S in there for Superman. He looks like Clark Kent, wears nerdy glasses like this, and his hair is all spiked up on the front. But